So this is day 2 of 10.1. Yesterday we just introduced a bunch of vocabulary, just getting comfortable with some new words that we're going to use a lot this chapter, all about circles. Okay, so we're switching gears a little bit. Today we're going to take some of that vocabulary and apply it to some new theorems, okay? Now, one thing to keep in mind when you're looking at these theorems is what some of they kind of have in common. They're all, for the most part, involving one kind of idea, okay? So just keep that in the back of your mind. The other thing to notice is none of these theorems have names. Right? We've learned when we have theorems that have no names, okay, if we ever had to use it in an explanation or proof, we just have to kind of do what?
Just describe it.
Describe it. Kind of summarize it. Most of the time, if the theorem doesn't have a name, that means we're not going to use it in a proof very much. Think about this chapter or this whole semester, very little proof, okay? And it's still that way. So we're going to use it more just to apply it. All right, so this first theorem, notice it's an if-then statement. It also has a picture attached to it, so make sure we're kind of understanding what the picture means. It says, if a line is tangent to a circle. Okay, so a new vocab term from yesterday. Refresh my memory. What does that mean if it's a line is tangent to a circle?
If it's tangent, it will only touch the circle at one point, which is our point of tangent.
So this, I'm going to just make a little note. It basically intersects
the circle.
If I can spell. A circle at one point. Okay, just a little refresher. All right, so in this picture, which line do you think they're talking about?
They're talking about line M.
Okay, so this is your tangent line. It says then it is your tangent line, so the line M is perpendicular to the radius. Okay, perpendicular to the radius drawn to the point of tangency. Okay, so let's think about what that's basically saying. All right, so if I give you a line that's tangent to a circle, it will end up being perpendicular to the radius as long as the radius is drawn to the point of tangency. Because here's the deal. A circle has lots of radii, right?
Right.
So I could draw in a radius here, but that wouldn't necessarily be perpendicular to that because it's not even intersecting it.
Right.
So kind of keep that logic in mind. So in this picture, essentially what you're given, and I always like to write this off to the side. So if you're basically given line M is the tangent line. So line M is tangent
to circle Q.
To circle Q. I like that you said that. Then what can we conclude?
Then segment QP is perpendicular to line M.
Now, so this is the radius, and this is your tangent line. Okay, if I actually, gosh, I'm having a hard time with this today. So if I actually kind of drew that in the picture, that would mean this is perpendicular.
Right.
So that's probably going to kind of lead into some other ideas, which you'll see in just a minute what that means. Okay?
Yes. Now, this next theorem that you're going to see, it says if in a plane, if a line is perpendicular to a radius, so here we've got a line perpendicular to a radius of a circle at its end point on the circle. So what this is saying is that if I have this line M and I know that it's perpendicular to this radius at the end point of that radius where it's touching the circle, then the line is as I just crossed through that, the line is tangent to the circle.
Okay, so this is what I'm thinking while you're seeing this or saying this. And first thing I notice is the picture looks very similar to the last one.
It does.
And then I'm thinking, while you're saying this, it kind of sounds like backwards to what we just read. And so if you think about it, the if-then statement before was your conditional, so this would be the converse of the last one.
Exactly. So if you know that you have a perpendicular, so I'm just going to write that off to the side. So if we know that
segment QP is perpendicular to line M. Now, we're not given line M as the tangent. We're just given it's a line that is perpendicular to the radius at the end point again on the circle.
Yeah.
Then we can say that line M is a tangent line. So.
Love it.
Keep in mind, guys, if let's say that line intersect or was perpendicular at the other endpoint, let's say that happened.
If I could even touch it. That's awful. Okay.
If that happened, if that was perpendicular, well, that wouldn't prove as a tangent because it's intersecting
at 2
2
points.
points. That would be a secant. So
And there'd be no special relationship other than that. All right.
All right, here's another theorem. It says if two segments from the same exterior point are tangent to a circle, then they are congruent. Okay, so if two segments, now first of all, in this picture I actually have
Lines.
lines. But remember, line or segments are part of lines. So what we're really focusing on are the segment parts, because if you talk about reading on, you're talking about congruent, lines can't be congruent.
Right.
So what segments am I talking about?
Okay, two segments from the same exterior point.
So the exterior point would be
The S, it's outside of the circle, and they're tangent to the circle. So we're talking about SR and segment ST.
And notice the segments you're talking about come from the exterior point. And then what do we call these points? If these are both tangent to that circle.
Those are the points of tangency.
Okay, so when you're talking about the same exterior point and basically the segment formed between the point of tangency, and I'm going to make a little note. So point of tangency. Okay, because you could have a point here, but that wouldn't make any sense for the scenario we're dealing with. So it goes from the point of tangency to that exterior point. They're saying then those segments are congruent. So that means RS and TS, those segments are congruent. So let me write off to the side. I'm going to go back here real quick. If two segments, so the segments we're talking about RS and TS, segment TS, are tangent to what, circle P?
Circle P. And notice they're tangent to the same circle.
Mm-hmm.
They're not just two random tangent lines. They're tangent to the exact same circle.
Then we can say that they're congruent.
Wonderful.
Now, are these common tangents?
Are they common tangents? No, because that would require there being two circles.
You're exactly right. Now, one thing more real quick, guys. I want to show you why this comes about. Okay, just a quick semi-proof. If I draw in the radii to the point of tangency, what's true about the radii and the tangent line?
That they're perpendicular.
Okay, so these would be perpendicular, all right? And if I draw in the distance from P to S, the exterior point there.
We have two right triangles.
Right? So here's the deal. What's true about all radii?
They're all congruent.
So these are going to be congruent. And then they share a common side, and then they have a right angle. These triangles are going to be congruent because of HL, which would then prove why this segment is congruent to this segment. So just kind of a semi-proof of why this comes about.
Isn't it awesome how all these things tie together?
All connected. I know. It's so crazy. This was going back to like chapter 4. I mean, so long ago. All right, we have one more theorem, sorry.
No, we don't.
Oh, we don't. That's it.
No, we're good.
Okay.
We're just moving on to some examples now.
But before we do it, notice all 3 of the theorems dealt with tangent lines. Did you notice that? All of them had something to do with tangent lines. So that's something important.
Okay, the first one says, is segment CE, so this segment out here, is it a tangent? And again, notice it's part of a line. There's just a segment, but it's part of a line to circle D. So if that's true, we would call point E here the what?
It would have to be the point of tangent if it is.
If it is, and we don't know yet, but that's what we're checking. So, and that means that would be the only spot that line, if I continue it, would ever touch that circle.
That's because essentially tangent means it intersects the circle at one point. That's really what it is.
Right.
Line or segment or ray.
Right. So now, let's go back and let's think about the theorems that we've talked about today. Because I see a triangle here. And I notice that I've got a radius of my circle. And I've got a length of this segment that we're checking to see if it's a tangent. And they've given me another piece of this triangle, and they probably give me this for a reason. So let's think back to the theorems that we've talked about. In terms of something being tangent to a circle, what does that tell me?
Well, if we're trying to decide if it is, because we don't know, the only way to decide if it is if the tangent actually ends up being perpendicular to the radius.
So if that's true,
then it would be a tangent segment.
Right. Okay, so how could I check to see if that's the case?
Well, to show if it's perpendicular, we would, thinking about that this is a triangle, we would have to decide if it's a right triangle.
All right, so we are going to be using what?
We're going to use the Pythagorean theorem converse.
So we want to see, does 45 squared equal the 11 squared plus the 43 squared?
Now, notice this is a question I get every year. Notice where that 45 is labeled. I don't know if you get this. Sometimes people are like, what is that attached to? All right, 45 is that whole segment DC. And notice how I have it drawn there, okay?
Oh,
yeah, it's
I'll fix
connected.
it. Okay.
But basically, if it was anywhere else, for example, could it be the radius?
No, because the radius is 11.
11. So could it be that segment? It could be, but notice because it was labeled kind of right in the middle of it, all right, kind of right there, that's saying that whole segment.
Right. Now, good point, though, because if it had been out here, this whole segment would have been the 11 plus 45. But you would notice it would only be marked out in that little space.
Yes.
When it's in the middle, it's the whole thing.
Okay. Just thought, I was thinking about that because I get
That's
that question
a
a lot.
great question.
All right, so 45 squared is 2025. And we're going to see, does that equal, and then I'm just going to do 11 squared plus 43 squared all at once. Can I do that?
Uh-huh.
That's 1970. So obviously those are not equal.
Therefore,
So
that is not right.
So then, is the segment CE tangent to circle D? I would say no. And here's the deal. If they asked you to explain, which we often have you do, I want you to think about how to explain this, all right? We found out that it wasn't a right triangle, so I would say no because triangle DEC is not a right triangle. And why is that? Why is it not a right triangle? Well, because, well, not why, but why does that prove that it's not tangent? So if it's not a right triangle, then segment EC or CE is not perpendicular to segment DE. So kind of this explanation, you would have to kind of explain, like, what did your work support? The not right triangle. And then, but why was that? That supports if it's perpendicular or not.
Right.
All right, now this particular example says segment BC is tangent to circle A. So before we move on, what does that basically mean? If we know that this is a tangent,
Then we know that BC is perpendicular to AB.
so I'm going to make a little side note. So that means segment BC is perpendicular to AB, and that's because AB is what?
The radius.
The radius. Okay, and again, the radius is always the distance from the center of the circle to a point on the circle.
And it's the radius going to that point of tangency, too. Okay.
Exactly. Now, the directions say find the radius. So essentially, we're trying to find what AB is.
Right.
Now, let's look at other things that we have labeled in picture and understand how things are labeled. So I labeled this R because that's your radius. That's our unknown, all right? This tangent segment is 28. Now, what about this 14? Kind of think about what we just talked about on the last slide.
Well, the 14 is only on the outside part. It's not like in the middle of that whole segment.
So, and here's the deal. Could this whole thing be 14?
It wouldn't make sense because it's the hypotenuse, which would mean it's the longest side, and in 28 is longer than that.
Yeah.
So
that's just not possible. So I want you to kind of keep that in mind. So the 14 is the segment that's outside of here. Now, what's this segment right here?
That would be another radius.
So what do we know about all radii in a circle?
They're all congruent.
So this would be also another R, right?
Right. So that whole segment is really like R plus 14.
And why would I want to kind of talk about the whole segment?
Well, because I'm probably going to be talking about a right triangle here, and that is a side of the right triangle. That's the
Perfect.
hypotenuse.
Yes, good deal. So we have a right triangle. We have, obviously, the unknown of radius is the piece that's in there, okay? So we're going to use what, since we know it's a right triangle?
We are going to use the Pythagorean theorem.
Okay, so when I do this...
Get ready for this one, folks.
Okay, so when I do this, I'm going to take my hypotenuse, which is...
The R plus 14.
Now, I'm squaring that, right? To show
Right.
that I'm squaring the whole thing, right?
Exactly.
And we know it's going to equal, because this is a right triangle. And what's it going to equal?
The R squared plus 28 squared. Okay, now let's go back to algebra for a minute. When you've got a quantity like R plus 14 that we are squaring, that really means I'm taking it times itself. I cannot just square R and square 14.
And let's say you did, because this is what a lot of
This is
people
the
do.
most common
So
mistake.
if you square the R and square the 14, you get 196. And then over here you get R squared. And then what's 28 squared?
Let me see. That would be 784.
So here's what's going to happen. You're going to, okay, I subtract r squared on both sides.
I'm
left with 196 equals 784. Well, that makes no sense. I didn't
It'd be a no solution.
Yeah. Well, we're going to be able to solve for r. So what I did there is completely wrong because there is no rule that you can square a quantity that's being added or subtracted.
Right.
All right. So going back to what Ms. Hogravy said, when you square something, that's saying take it times itself. So let me rewrite this sucker. If I rewrite it, and I write it as...
Oh, I'm thinking about FOIL that we learned in Algebra 1, or the distributive
which
property.
essentially means you're distributing. You're distributing your first term times its first term, outside term, inside last.
Right.
Okay, let me make a little side note. FOIL. So why don't you guys, because I know it's been a while, but I want to see if you can remember this. Go ahead and distribute through and see if you get the same thing as us. Okay, so if I do first times first, so r times r is r
Squared.
and then I go to my outside
R times 14 is 14r.
and my inside
Another 14r.
and my last term.
196.
And then over here we said r squared plus, was it 784?
784.
So notice when we did that, notice what happened is we don't just have an r squared and a 196. We have these two terms here. And when I combine those, I'm going to go ahead and get 28r. Hopefully this is ringing a bell. Light bulb came on. You're like, oh, I do actually remember something back from last year. All right, your Algebra 1 teachers will love you. All right, now our goal is to find the radius. So at this point, what am I going to do?
Well, okay, I'm going to think back for a second to what you said before. If I subtract an r squared from both sides, those r squareds will cancel each other out.
Which is kind of convenient because if you think about it, guys, and we're going to see this a lot in this chapter, these are essentially quadratics. A quadratic, the approach to solving it's going to be a little differently than a linear. But since the r squares cancel out, you can be left with basically a linear equation, which is super easy to solve.
Right.
Okay.
So now we can go ahead and subtract a 196, which is going to give us a 588, and then divide by 28, which would give us 21.
And now, here's the deal. This is where you want to think logically, too. Would it make sense for this radius to be 21? Well, if I put 21 here and 21 here, that's going to make this side, what, 35, right? Would 21 squared plus 28 squared equal 35 squared?
And then it works.
And it works. So we're good.
All right. So now we have that AB, this is, again, a segment that's outside of the circle. It looks like it's got a point that's on the circle and another endpoint.
Well, it says it's a tangent.
Oh, it does say it's a tangent. It's tangent to the circle. So we know that it touches it at that point of tangency. And the same thing with AD. All right. So AD is a tangent to circle C, and AB is a tangent to the circle, and again at those other endpoints. We learned a theorem that will help us out with this significantly. Because what do we know about any two segments that are tangent to the same circle and have an endpoint that's common at a common point outside the circle?
That they're going to be congruent segments.
Wonderful. So I'm looking at this and I'm thinking I could probably write an equation now.
Yeah, since they're congruent, we can set them equal.
And that's going to be a x squared minus 4 is equal to
21.
Awesome. Now, we've got a quadratic equation here.
Yes.
I'll tell you that this is one of those basic quadratic
Yeah.
equations that you can solve without having to factor, without having to use Pythagorean theorem, without having to use quadratic formula, because we don't have any x's also. We just have x squareds and constants. Let's get all the constants to the same side.
Yeah. So add 4 to both sides. And then we can go ahead and take the square root to both sides. Now, here's the deal, guys. Because I like that you brought up, it is a quadratic. How many solutions do quadratics usually have? 2. So let's put plus or minus 5. Now, sometimes we found that only one worked. Sometimes only the positive. Sometimes only one works. So let's check to see if we could have both. So if I have 5 squared, that's 25. Minus 4 does get you 21. So that works.
So 5 definitely works.
If I do negative 5 squared, notice how she puts parentheses around it, minus 4, that's also 21.
Yeah, because
So-
don't forget, when you take a negative number and you square it, you're taking a negative times another negative, which does make it positive. So they both work. So really both positive and negative 5 are solutions here.
So just be careful with that.
Yeah.
We're going to see more quadratics, and we're going to talk about that, the factoring and quadratic formula idea in just a little bit.
Right. And so anytime that you square root to undo a square, don't forget to put the plus or minus piece out front.
Yes. All right, last problem. It says find the perimeter of the hexagon knowing the following. Okay, so we're finding the perimeter of the hexagon.
So the hexagon is this shape on the outside, but I noticed that there is a circle that is inscribed
Okay.
in it.
Now, let's just make sure we're good with what perimeter means. Perimeter basically means...
Add all the sides.
Okay, so if I know all the side lengths, I can add them up. I'm good to go. Now, here's the deal, and I like that you pointed out. There is a circle inside of that hexagon. Notice the relationship between that hexagon and that circle. Notice how every single one of these sides basically
Is a tangent.
is a tangent to that circle. It's intersecting the circle at all of these points here. Okay,
Okay.
so each of these sides, I'm going to make a note, these sides are tangents. Okay, so we want to keep that connection. Again, this whole day has all been about tangents. What do we know about it? Okay, and here's the deal. We don't really have any radii drawn in here, so we're not talking about tangents being perpendicular to anything.
Right.
So really, we're going to be probably thinking about one particular theorem. We'll talk about that in just a minute. All right, let's go ahead and start labeling the stuff. That's what I'd start. So they gave you segment AB is 2. Now, segment AB is not an actual side length, but it's part of a side. GF, same deal, part of the side. KI,
It's the whole,
this
that
whole
is a
thing
whole
right
side.
here. That is a full side. I was looking up here. I was like,
That's
where's
8.
KI? And then IG is a whole side as well. So that helps a little bit. FE is 7. Now that's going to give you a whole side, isn't it? So I'm going to go ahead and just do that. That whole side is
15.
15. What am I missing? CE is 16. So I technically have 4 of the 6 sides. I don't know anything on this one, and I need something over here. So what do we know about because this is probably something we got to know because that
Right.
relates to what we've been talking
The fact
about.
that they're tangents, well, we've got some points that are outside of the circle, like common exterior points that are segments with the point of tangency.
So, like, for example, let's kind of talk about what she's meaning. So, like, point A is outside of that circle, all right? And if I connect it with point B, this is considered a tangent segment, all right? Point A shares it's common with this segment here, LA. You see that? And again, I'm going from the point of tangency to that exterior point. If you remember back to that theorem, let me find it. Where's it
I want
at?
to say it was on 3, but I could.
Yes. If you have a segment, 2 segments that come from the same exterior point to the point, the tangent, point of tangency basically, for both of them, what was true about them?
They were congruent.
Okay, so that means AB would be congruent to
AL.
AL. So that means this is also
2.
2. So let's use that. Let's go around and I'm going to find some of those segments. Like down here, FE, segment FE is 7. That's going to be congruent to segment
DE.
DE. So that's 7. Now that's going to help you find CD. How would I help?
So that should be 9, because really the 2 together make up 16.
16, which that will help you find,
CB,
which because those are going to be the same. So this is
9.
also 9.
Ooh, there's another side we know now.
All right. So we have 5 of the 6 that we need. We need one more.
Okay.
So let's go over here. Okay. I don't know anything here, so I'm gonna go over here because I'm gonna work my way. Notice how I started here and I worked way around. So I'm gonna start here. GF is 8, so that means
That GH is 8, which means that HI would be 5.
because these two add up to 13.
So JI is 5, which would leave KJ to be 3, because those two add up to be 8.
Which means
KL is 3.
because
So
these are congruent. So that means this
that
side
side.
is
5.
all right. So now we still got to find the perimeter. Okay. But notice, guys, there wasn't like a lot of work involved. It's the picture. I mean, to me, it's just labeling that picture. All right. So to find the perimeter, you're basically adding 5, 11, 16, 15, 13, and 8. I got my handy helper here.
Should be
typing
68.
it. and the perimeter is 68. Hopefully you got the
Hopefully
same
I
thing.
typed that in right. Yeah. Okay.